Welcome, welcome, welcome. I'm Lisa Blackburn. This is my YouTube channel for everything I like to talk about, science and math. And today we're talking about gases, the gas laws. So this is Unit 9. We're getting close to the end. Yay! And y'all already know a lot about gases because you breathe air, you've lived your life. This one's going to be pretty common sense. Okay, so gases exert something on their surroundings. What do you think it is? What? Themselves. And how do you feel that? Air. And it's pressure. They exert pressure. Let me get the little marker here. They exert pressure on their surroundings. You're familiar with atmospheric pressure. And the symbol you need for pressure is a capital P. So fill that in. I left it off of your notes. You live in a sea of air. You're under tremendous pressure right now, but you're used to it. You've lived your whole life in this air. You don't even think about it. You don't even feel it. But right now, the atmosphere is pushing down on you with tremendous pressure. So how much pressure do you think it is? So PSI, who knows what PSI stands for? People who work on cars and stuff. Anybody know what PSI stands for? It's pounds per square inch. It's what you fill your tires up. You ever read on your tire and it tells you how many PSI you put in there? It's how much gas you put in it. So pounds per square inch. So everybody look at your palm and look at an area of 1 square inch. Okay? Right now the atmosphere is pushing on that inch. How many pounds of pressure do you think it's exerting on that 1 square inch? What do y'all think? How much? 3, 9, more than that. It's not that much. It's 14.7. So in that 1 little square inch, there's 14, almost 15 pounds. Think about how much 15 pounds weighs. But you're used to it. Okay? So now, think about your stomach. Your stomach is a square foot. How much pounds of pressure do you think just the air in the room is putting on 1 square foot on your stomach right now? It's over 2,000. 2,000, whoops, the 2 went away. It came back. 2,116 pounds per square foot. You have 2,000 pounds, as much as like a little bitty car, on your stomach right now, but you're used to it. Your whole life, the air has been pushing on you, you've been pushing back, and it feels normal. But what if we were to take you without a spacesuit and throw you into outer space? What would happen? You'd die because of lack of oxygen. But say you're Jimmy Neutron. I don't know if y'all ever saw that really old Jimmy Neutron movie where they get into spaceships that are open and they go fly into another planet to compete on a game show. It's weird. But they just go flying along without a spaceship, and the oxygen doesn't seem to be a problem. But what would happen as far as pressure would go? What would happen to you?
Pressure would be too much, and then you would, I don't know.
Would you crush or pop like popcorn? Pop like popcorn. You would explode. You would be pushing out, but the atmosphere wouldn't be pushing back. Right now you're in balance, but that balance would be disrupted. So you would pop. Now we see this with fish. Fish at the bottom of the ocean are at much higher pressure than we are. So when they catch these fish that are supposed to be, way down deep in like Mariana's Trench kind of thing, that they bring them up to just 1 atmosphere, they will kind of pop. Their guts come out their eyes, out their nose, out their mouth, just out their gills, they just out their anus. So you can see pictures of this. It's on the internet. But these fish, they don't really pop like a piece of popcorn all over. They pop at the weak spots. The eyes, the mouth. It's rather gross. So that's what would happen to you if we just threw you out in space. Good thing we're here in our atmosphere that we're used to. Now, These are English units, inches and feet, so we don't use those in science class, but we use them in real life. And that's why I always introduce this with English. You know what an inch is. You know how heavy a pound is. So you can imagine 2,000 pounds on your stomach, what a huge pressure that is. But in science terms, these are the things, at 1 atmosphere, the amount of pressure on you right now, more or less, it's 1 atmosphere at sea level. So we're a little above sea level, so we have just a little bit less pressure on us than an atmosphere. But in science terms, 1 atmosphere equals different units. And the reason why there's a bunch of different units is this was one of the very first areas of chemistry that was ever studied was gases. And at the time of development, they came up with a lot of different units for pressure at the beginning. So one of them is called millimeters of mercury. And 1 atmosphere is equal to 760 millimeters of mercury. What that means is, look in your notes. Do you see that science device that's over to the side of these notes? That is a barometer where the atmosphere pushes on the bowl of mercury, and if it pushes harder, it pushes the mercury up that tube. It goes up higher. It's more inches or millimeters of mercury. So pressure, atmospheric pressure, is measured in that. And our atmosphere changes. So like if we were suddenly going to have a low pressure, suddenly there's not much atmosphere pushing on that bowl of mercury and the pressure drops. Are we about to have clear skies or a storm? Y'all know? It's a storm, and this is how you remember it. The highs, they bring clear skies. So if you have a high pressure, it's a beautiful sunny day. If you have a sudden low pressure, this is a storm. And the bigger the low, the worse the storm. So like, I remember one time we actually had our hurricane reach all the way up here. Hurricane Opal. It caused an extreme low pressure because this hurricane made it all the way to Atlanta. And all the ladies who were close to being born, to having their babies be born, suddenly there was a low pressure and the babies popped out. So one of my children have all these friends who have the same birthday weekend, because any lady who was within probably 4 weeks of having their baby when Hurricane Opal went over, they had the baby. It was such a low pressure, it triggered labor, and all these ladies had babies. So there was hurricanes make birth spikes. And so one of my friends, one of my son's friend's mom, said that she was on the phone with her mom, and she's having the baby, and her mom is yelling at her, "Why are you having a baby in a hurricane? I can't even come. It's a hurricane in Atlanta." And she's like, "Mom, I can't help it, and this baby's coming. There's no stopping it." So watch out for hurricanes if you're pregnant. You'll go ahead and have that baby. All right, so millimeters of mercury, or we also do inches of mercury, are one way of measuring. Millimeters of mercury are also called torr. So another pressure unit you'll use in science is torr. It's the same thing as millimeters of mercury, same number. Another one is pascals, but we don't usually use regular pascals. We usually use kilopascals, like just how with other things like kilograms we use a whole lot. Kilopascals is something we use a lot, and it is 101.3 kilopascals is equal to 1 atmosphere. Another one that you see is bar, and I've left that out, so go ahead and write it in. And it is the same number as kilopascals, you just move the decimal place. It's 101.013, but it's the same number. So a lot of these, we got a little message on there. I'm touching you who is watching. A lot of these are the same. So a lot of times, the first kind of math problem we're going to do is we're going to have to convert between pressure units. So we're going to do a few of those to start with on this problem. Example, the pressure of a tire is 28 psi, pounds per square inch. So you see pounds per square inch like this. Oh, there's 1 pound per inches squared, pounds per square inch, but it's more common to see it psi. So this is a more science way to write it, but this is how you see it more often, like on tires. Okay, the pressure of a tire is 28 psi. What is that in atmosphere? Torr in kilopascals. So we're going to do 3 little conversion problems here. So whenever you do a conversion problem, you start with what you know, right? So we're going to do it 3 times. So I'm going to write 28 psi, 28 psi, 28 psi, because I'm doing the problems 3 times. Okay, the first one I'm supposed to do is atmospheres. What do I write in the denominator always? PSI, what I know, right? So y'all are getting good at this. This is going to help you a lot next year in physics, because physics problems are all, you do them just like this too. All right, now, what is the relationship between PSI and an atmosphere? What's our conversion factor? How many PSI are in atmosphere? What?
14.7.
Right, so 1 atmosphere is 14.7 PSI. What about torr? What is the relationship between torr and an atmosphere? And since 1 atmosphere is the same as 14 PSI, we can instead just go ahead and say that it's 760 torr. Does that make sense to you? That relationship is also the same, because because this is 1, because it's 1 atmosphere, they're both equal to that 1 atmosphere, then this is the relationship between each other. 760 torr is 14.7 psi. They're all equal to the same thing. And what is the relationship between kilopascals? What number do I need?
101.3.
101.3. And really, this is the most common unit for gas problems. For chemistry gas problems is kilopascals. That's the one you usually see, is the 101.3. All right, so now what do you do math-wise? What do you do to any number on top? Multiply any number on bottom? Divide. So try it on your calculator, see if you get what I got. I got 1.9 for atmospheres. I got 1,447.6 torr. Now you do see millimeters of mercury and inches of mercury on the weather. When they report the weather, because there's that connection between weather and air pressure, I think you do hear inches of mercury, I think is what they reported on the weather. Okay, and then for the kilopascals, I got 192.95 kilopascals. Pascal was a scientist who discovered a lot with gas. So he got a unit named after him. Blaise Pascal. Okay, everybody got those when you tried it on your calculator? I did them fast, so mine could be wrong. Let me know if I did it wrong.
You did them all right.
I did them all right. Yay, go me. I think the pressure's weird today. It's kind of giving me a headache a little bit. Did any of y'all get that? Get a headache when it's going to storm? Because it's a rainy day, so that means we have a low pressure. All right, now we have been over this before, but it has to do with what we're talking about. We're talking about the kinetic molecular theory. What controls gases is the fact that they're in motion. So there's the kinetic molecular theory of gases, and because gases are a state of matter, we're going to review it. I expect you already know this. The phases of matter. So this is going to be an easy part of the test. Which state of matter has the particles are in the crystal lattice? It has a definite shape and volume. It has lower heat and energy, and the molecules can only vibrate. What's that? A solid. Y'all are brilliant. Okay, number 2, or letter B. The molecules are free to move. They take the shape of its container. They have a definite volume. What's that one? Liquid. The molecules are free to move faster. They take the shape and fill the container. They have high energy or heat. What would that be? Gas. And then they have high energy. They move very fast. They're in fluorescent lights and in stars. What's that one? Plasma. So we have some in our room right here. We have fluorescent lights. We have our sample of plasma that we can always refer to. All right, that's easy, right? Everybody knows that. So you can match those to the drawings. Now, the relationship between vapor pressure and boiling. So you have a drawing of a pot with some bubbles, and then some bubbles boiling up there. Okay, so how boiling works. Have you ever noticed when you're watching a pot for it to boil, that it'll get some bubbles on the bottom, but it's not boiling yet? Have you ever noticed that? The reason why is for it to actually be boiling, what happens is some of the heat goes into the liquid and it vaporizes part of the liquid and it makes a little gas bubble. But until that gas bubble reaches atmospheric pressure, it won't boil. So it'll stay there, getting hotter and hotter until and it's trying to boil, it's trying to push up and out, but the atmosphere is squishing it down and keeping those bubbles from coming up. When they finally reach atmospheric pressure, then they can boil. Boiling doesn't happen until the bubbles reach atmospheric pressure. Does that make sense to you? Can you imagine that? You ever wondered about that before? There's bubbles. Is it boiling? No, it's not. It's not there yet. All right, this is called a phase diagram, and you have to be able to label it, understand it, read it, use it for the test. What it is there is a relationship between which state of matter something is in, pressure and temperature. Do you see how pressure is on this side in atmosphere? Temperature is on this side in degrees Celsius, so it changes right there at 0. And this is a phase diagram for water. So every chemical would have their own phase diagram. It would look different, but this is one for water. Joseph, put your phone away. Unless you're taking my picture. You want to show your mom your crazy science teacher? I understand. All right. So if something is below 0, it's usually an ice. It's ice. Water usually is. But if the pressure is very, very low, even at 0, it can still be, it can actually it can sublime. This is where it would go straight from ice to water vapor without melting first. Remember I told you my story about the snow day where the snow just disappeared? The air would have been dry that day and it was probably a low pressure still. So it was able to, it just sublimed. It went straight from ice to water vapor. Then up here, usually above 0, it's melted and it's water. But if the pressure is very, very high, it can actually stay water even though it is below 0. And also, right at 0, sometimes it's confused and doesn't know what to do. So that's when you can take your water bottle out of the very cold refrigerator, smack it on the bottom, give it that extra energy, and it'll go and turn into ice. Have y'all done that? You get a water bottle that's right at freezing. It's all over YouTube. You can find it. There's people doing it with other drinks too. Thank you, ma'am. We're doing notes. You can grab them on your way back to your seat if you want to. And there's also the homework up here too. Okay. So anyway, this is, depending on, so the triple point is the exact pressure where you can have ice and water vapor all together, and it's sort of like will change between those three things. All right, so does this diagram make sense to you? And if I ask you a question, like I said, at 100 degrees Celsius and 218 atmospheres, is water ice, water, or water vapor? You would go up here and go, oh, it's liquid. Do you see how to use the chart? If I give you the chart, you can label it and use it. Okay, we're going to do a lab on this tomorrow with dry ice. So that'll be fun. We're going to play with dry ice. We're not going to get burned. Cold can burn you too. So that'll be tomorrow's lab. All right, let's find the button. Button, where's the button? There's the button. All right, gas laws. Now there's a song for this. The gas laws are good to know. You can use them everywhere you go. We're talking PV equals nRT. We're talking heavy duty chemistry. I know it's great. I'll sing it more later as we do this unit because it gets in my head. All right, so this is very important. See how it says important? For gas law problems, temperature has to be in Kelvin. So if it's given to you in Celsius, step 1 is add 273 degrees. Now, little help for you. On the back of the periodic tables I let you use for the test, this is there. It is written on the back as one of the facts. So is at least some of these formulas. So if you forgot some of your formulas, I know some of them are on the back of those periodic tables. So this week as we're doing math, like today, as you're going to be working on that first gas laws math worksheet, you should get one of my periodic tables and look at the back and see what information is there for you already and what you're going to need to memorize. All right? More than just flat out memorizing all the formulas, even there will be a part of the test where you match the name of the formula to its formula. I want you to be able to use them. So, all right, so the first formula has to do with temperature and volume. This is Charles's law. This was his last name, not his first. Dr. Charles. He came up with this one, and it's the relationship between temperature and volume. If you have a gas and you increase the temperature on it, so imagine I've got a Mylar balloon here, and it's a little bit old. It's that point where it hangs like right about a meter above the floor. It's a little crinkledy, but I put it on some heat and fluff it out. I said the answer. I put out some heat. What will happen to the balloon? Will it get bigger or smaller if I heat it up? It'll get bigger. So when the temperature of a gas goes up, the volume goes up. Does that make sense to you? Okay, now what about if I took my balloon and I put it in the freezer? The temperature goes down, what's going to happen to the volume? It's going to go down, right? That balloon will shrink. Has anybody ever seen that happen? You had a balloon, it was down in your kitchen overnight in the winter. You're one of those winter birthdays, and you go down in the morning and it's all shrunk because it got cold overnight. I've seen that happen. One of my kids has a January birthday. All right, so this is the formula. I had to write it like this because Word is not very great for chemistry. And so I had to do sideways fraction bars. I like this written better like this. V1 over T1 equals V2 over T2. So how these problems are going to work, and I want you to write it like that, not like that, is you are going to be given 3 of the 4 variables. You cross multiply and solve for the one you don't have. So easy. You learned how to do that math in 8th grade, right? Cross multiply and solve for x. If you didn't learn how to do it in 8th grade, guess what? Today's as good a day as any to learn how to do it. I'll help you. Okay, so all we have to do is cross multiply, solve for x. Okay, the next one is Boyle's, and his has to do with pressure and volume. So you've got a little balloon, and you squeeze it really, really hard. Is the balloon going to get bigger or smaller? It's going to get smaller. You're going to squeeze it. The pressure is going to go up. The volume is going to go down. Does that one make sense? I bet this is the counselor wanting somebody. Yep. Hello. I do. Yes, I have Carter.
I got
Yes. Oh, thank you. Carter, you have to go to Dr. Haston's office.
I don't know who that is.
I don't either. Anybody know what that is?
No.
I'm new here.
Go to where like that, you know where the counselors are? Okay, just go in there and then just say, can I see Dr. Haston? Or Dr. Haston called for or something. Because it's
Yep.
the lady at the front of the counselors.
Okay.
I know where the counselors are. They're near the media center.
Across from the nurse.
I'm feeling proud that I'm learning my way around. All right. So if the pressure is down, say that you were able to put a balloon in a vacuum chamber, what would happen to the volume? It would go up, right. So notice that this is a direct relationship. Temperature up, volume up. This is an inverse relationship. Pressure up, volume down. Pressure down, volume up. Notice that with this one, where it is direct, that there are fractions here. For this relationship where it's inverse, it is not fractions. Does that make sense to you? There is a relationship between it being a fraction and whether it's a direct relationship, one goes up, the other one goes up, or inverse, one goes up, the other one goes down. We all right with that idea? Sometimes when I say the word fraction, people get a rash or cry. So I'm just making sure we're all okay with the F word, fraction. Right? Good? Okay. Yes. I used to have one girl I tutored. I tutored her for 4 years. And the first time when we first started working together, as soon as we would do math, anytime to do math, big tears just rolling down her face. She would just cry. You just get the math out. Before you even look at the problem, big old tears. After 4 years, I was at her graduation and she spoke and she thanked me as part of her speech. And she said, "Thanks to Miss Blackburn, I don't hate math anymore." She never said she liked it, but she didn't hate it. I was like, oh, proud moment as an educator. This girl stopped crying over math. She didn't hate it anymore. Okay, so the next one is Dalton. I always think of that like Dalton, Georgia, but Dalton. And it's that pressures add up. So, say you've got a can with tennis balls. You know how those come under gas pressure? And they squirt a little air pressure in there. But then they wanted to add some other gas to make sure that they're, pH balanced. So they stick that in there. Well, those two pressures would add up to be a new total pressure. The more times you squirt a gas in there, those pressures add up and up and up. And that's what he thought of. So if you have greater density of gas, it will have greater pressure. So here we have our total pressure you get by adding up all the pressures you put in there, and those are called partial pressures. So however many you have, that's why it's dot, 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 dot. However many you have, you add them up to get the total. Is that one all right? We can do that? Okay, it's just adding. The next one is Gay-Lussac. So it looks like Gay-Lussac, but I think you pronounce it Guy. Don't know much about French, but I think it is. And this one is pressure and temperature. Okay, so imagine this. You have a container of gas. You heat it up. Is the pressure inside the gas going to increase or decrease? If you heat it up, it's going to increase, right? The pressure, the temperature goes up, the pressure goes up. The temperature goes down, the pressure goes down. Now notice the little drawing over here with fire with a keg on it. So a keg is a thing people buy a bunch of beer in. I don't drink alcohol, but I've seen them before, so I know about this. And here in Georgia, sometimes we are a little foolish, maybe not as smart as some other areas of the country. I'm not saying that, but it could be true by this story. So up at Lake Lanier one time, there was a bunch of people who were having a party, and they had a keg of beer, and they drank it all. And then they had a campfire, and they decided to throw the empty keg onto the campfire. Was the keg really empty? No, it didn't have beer in it, but it had gas in it. So when this keg heated up on the fire, the pressure, because of Gay-Lussac, the problem was they didn't pay enough attention in chemistry class. This was a failure of paying attention in chemistry class because they threw the keg on the fire. It got hotter and hotter and hotter. It exploded. I think 2 of them died. It exploded like a bomb, shrapnel, killed a couple of people, other people severely wounded by flying hunks of hot metal. So failed to understand Gay-Lussac's law. Temperature up, pressure up can cause an explosion. And the thinner and lighter the material that explodes, the less catastrophic. Does that make sense? Less pressure will build up before it explodes, and it's not so dangerous. thick, heavy something like a keg can have tremendous pressure before it explodes. Y'all did did this. When we put the chalk and the vinegar in the little plastic things, we let the pressure build up. It wasn't temperature, but we let pressure build up from a chemical reaction. It exploded. I knew nobody was going to die because the containers I gave you were very flimsy, weren't they? A few of them even didn't make it through the day. A few ended up in the trash. So nobody was going to lose an eye. You might get a little vinegar on you, but it was all in good fun, wasn't it? Nice little exploding chemicals. All right. The next one is, so this one too, I want you to write it. P1 over T1 equals P2 over T2. Flat fraction bars. The next one is the ideal gas law. That's the one I sang about. PV equals nRT. Okay, so here it is. PV equals nRT. We're talking heavy duty chemistry. And it is that the factors are all interconnected. We're going to say they all interact. They all interact. So you can put all of the things into one formula in a certain situation. And if you know 3 of these, you can solve for the 4th one. It has a constant. So N is the number of moles, and you might have to use Avogadro's number to convert something to get that. But R is a constant. And this is it, 8.3140. That's its liters times kilopascals divided by moles times Kelvin. So once again, it has to be in Kelvin. But we'll do problems with that. It's just the same thing. I'll give you all the factors but one, and you just solve for X for the one you don't know. All right? That's not too hard, right? Okay, the next one is the combined gas law, and it is pressure 1 times volume 1 over temperature 1 equals pressure 2 times volume 2 over temperature 2. So sometimes there's 6 variables. You'll be given 5 of them, and you have to solve for the 6th. And it's that there is a relationship between pressure, volume, and temperature, which you can tell from all the gas laws, right? All right, any questions about that? The gas laws are going to be just fine, right? This is going to be great. We're going to get to play with dry ice, do other experiments, do a little math. Okay, now what makes up our sea of air? Approximately 80% of our air is what gas? You're going to breathe it in right now. No. Nitrogen, right. If it was the other way around, we would all die because we would have a spark and the atmosphere would catch on fire, everything would burn. So it's nice, inert, doesn't burn at least, it's not completely inert, nitrogen, nice putting out fires nitrogen for 80%, and 20% is oxygen. Now, of course, these are rounded off because you know there's other gases. There's carbon dioxide, there's a little bit of helium, argon, krypton. There's other gases too. And a big one that we talk about is ozone. Does anybody know the formula for ozone? It's O3. Instead of O2, it's O3. And it's very important. It's a shield for our planet. It helps protect us from UV light, and it actually is part of what helps deflect things. The atmosphere helps protect us from like asteroids and stuff. But students get the idea that because they hear there's a hole in the ozone, they think, oh no, there's a hole in the ozone, we're all gonna die because there's a hole and there's nothing we can do about it. But it's not true. Our planet is so terrific, it renews the ozone layer. It had a plan for if there got to be a hole in it, how you get more, and it's lightning. Lightning is what makes ozone. Have you ever smelled right after lightning strikes where you were close enough to smell the lightning? It's a very particular smell. We can hear, we have thunder going right now as I'm talking about lightning. It's just coming together perfect. There's always one. There's always one down by a little bit bigger one down by the south Pole and a smaller one up at the North Pole. We don't know if it's always been there and it's just something natural. It gets bigger and smaller though. So there was an idea that the hole was man-made by pollution. And in particular, we know that there are chemicals that do react with ozone and destroy it. Some that were used to especially being aerosols. The problem is the ozone is the very last thing before space. Atmosphere, ozone, space. So it's way out. The chemical that can destroy it is huge, heavy chemical. It can't get up there. It's huge. It would be like, a lead brick flying up there, chemically speaking, and smacking the astronaut in the head. It would be very unlikely for a lead brick from Earth to fly up and just for no reason smack an astronaut in the head who's out doing a little spacewalk off of the space station. Chemically, that's why it appears that yes, the chemical in the spray cans does destroy ozone, but if it was the culprit, how was it getting up to the ozone at the South Pole? Not a lot of people down there spraying hairspray. If it was directly related to pollution, wouldn't it be over Beijing, the worst polluting city? Some of the cities in India are some of the worst polluters. We used to be real bad. We're doing a little better now because, trying to be clean, trying to save the planet and stuff. So anyway, it's a little bit of a mystery. So this is an area where we definitely need more science. We need to find out, is the hole in the ozone caused by man? If it's caused by man, what do we need to do to stop it? If it is the spray cans, those have been banned for a very long time. The hole's still there. So is it because those chemicals are in the environment getting churned up by storms? I don't know. There's just parts of this we don't know all about. But the ozone is important. It protects you from, it's what takes out a lot of the UV light. We would have lots of skin cancer. It would be very bad not to have this thing. So it's important. We want to make sure it doesn't get destroyed, but at least it can be renewed. So if we can figure out, if we're making a hole and we can figure out how to stop it, at least it's not forever, because there are storms going on all over the world producing lightning up where it would make ozone, and it would be then renewed up into the ozone layer. And that's why the hole grows and shrinks. And it seems to grow more in the summer and shrink in the winter. I don't know. Above my pay grade. I'm just here to teach. I'm not here to figure out all this stuff, but maybe you guys could be the scientists who figure it out. But on Earth, ozone is considered a pollution. It's very bad for you to breathe in. It's very bad for your lungs, and it's made by copiers. You ever smelled copiers going? They have a distinct smell. Well, that's the ozone. So if you want to smell ozone, it's not good for you. But of course, it'd be right over there in the teacher workroom where you sign in. Also after lightning. Now let's talk about lightning. If suddenly all the hair on your body starts standing on end, what does that mean? You're about to get hit by lightning. Lightning is attracted to whatever is the tallest thing and round on top. We're pretty tall, we're round on top. So suddenly all your hair starts standing on end. That means you're about to get hit by lightning. What should you do?
Run.
No. Flatten as flat as you can in the dirt as fast as you can. I don't care if it's muddy. I don't care if it's raining. Face down, boom, you flatten yourself. You got to not be the tallest round thing on the horizon. It happened to me one time. It had been raining. It was in the summer. It was tomatoes in the garden. I wanted a tomato. I thought, great, I'll go out there and go pick a tomato between storms. I got to the garden. Suddenly, all hair on my arm is standing up. I thought, oh no,